Hi, kids. Here we are on our continuity continuity lesson. So look at this little jagged algebra 1 type graph. And as you scan it from left to right, you can, I think, obviously see that it is not continuous, right? At 1, 2, 4. So identifying where something is continuous is great, but now I'm going to ask you to prove f of x is not continuous at 4. And I'm going to do a bunch of examples about not continuous, but I could also say, pick a point and say prove that this function is continuous at a point. I do want to emphasize that we are proving continuity at or not at a point, not overall, right? That's a slightly more involved to prove an entire function. So you are only going to be asked to show that a function is or is not continuous, but at a specific location. And notice we are talking functions. So prove f of x is not continuous at 4. Well, here's what I'm going to say. The function value at 4 is undefined, therefore not continuous. This is kind of like a duh, right? Right? Duh. The function doesn't exist. You can't be continuous if your function doesn't exist, right? So it's not just that there's a hole, it's that this function does not have a value anywhere at 4. So not continuous. But look what happens at 1. At 1, when I try to do the same thing, I try to say, well, what is f of 1? Whoops, sorry. F of 1 is 1, isn't it? But yet I can see, so the function value is defined because I have a closed circle. Why? I mean, I can see that I have a jump, right? Saying I have a jump is not a proof of non-continuity. Let me give you a hint. The function values as you approach 1 from the left, and the function values as you approach 1 from the right. What L word am I talking about there? Drum roll, limits, right? So no bumping bellies, right? The range walker here is walking towards a level of 0, and the range walker here with the big belly is walking at a level of 1, and the two cannot see one another. The limit as x approaches who? 1 of the function does not exist. Not continuous, right? Now I see a jump. I see a jump, right? That's what I see. But to prove, I have to write that the function exists, but the limit does not. Therefore, no bumping bellies. Therefore, the limit does not exist. Over here, I see the hole. And I say the function value at 4 does not exist at all, therefore not continuous. Uh-oh. Can you see what's gonna happen here? Even though I see, unlike, right? I see a hole. But step 1, the function value at 2 is what? Defined. It's defined and it's at 3. So now I go and I look at the limit. Do you have bumping bellies though? As you approach 2 from the left and as you approach 2 from the right, right? Look at my range walkers. They are both walking towards the same level. And what level is that? Uh-oh. But yet I know I'm not continuous there. I see the hole. What can you say? Right? And I will hint here. Oops, I'm already on pen. Right? The function value exists, but it is a level of 3. The limit exists, but it is a level of 1. I can't just jump to not continuous. I do have bumping bellies, right? I have a function, I have bumping bellies. However, the function level does not equal the limit. Therefore, not continuous. Right? So you see the 3 different scenarios there? For the first one, I only had to show that the function value did not exist. I could jump right to not continuous. The second one, we went over here and we did, right? We did 1. We did the function level existed, but the limit did not, right? The function value did not exist here. I jumped right to not continuous. The function level existed, but the limit did not. Therefore, I could jump to not continuous. Here, the function value existed, the limit value existed, but they were not equal. Therefore, I said continuous. Right? So, what about if I had asked you to prove continuity at 3? Right? It is continuous, but what if I asked you to prove it? Prove continuity at x equals 3. You would say f of 3, right? Step 1, f of 3 is 3. Then you would look at bumping bellies. They bump bellies at a level of 3. F of 3 does equal the limit as x approaches 3. Therefore, continuous. It's a little odd, but at endpoints, which is kind of a silly question, but every once in a while, I can prove those functions this function is continuous at the endpoint of x equals 0 and x equals, 5. By only, this step here would only involve the appropriate handed limit. So in other words, if I was proving continuity at the endpoint of 1, I would say, at 0, f of 0 is equal to 1. The limit as x approaches 0 from the right is also 1, therefore continuous at the endpoint. Oh, sorry, I have to say they are equal. There's me cheating a little bit. Okay. So, again, here are the steps for proving. Don't prove continuity don't go through this unless you see the word justify, prove, explain, show. First you see, does the function exist? Then you ask, does the limit exist? Then you show You ask if those last two values were equal. Then and only then can you say yes, continuous. Continuity fails if either one of those steps fail, right? So we showed the first example that I did, I showed that f of 4 did not exist, therefore not continuous. The next example I said was, well, f of 1 existed, but the limit didn't exist, so not continuous after step 2. The third one we did, I showed the function value at 1 existed, the limit value at 1 existed, but those two were not equal, therefore failed continuity here, therefore not continuous. Then the last example I did, I met all of these conditions, and therefore I could say continuous. So there's the formal definition of continuity. A function is continuous at an interior point of the domain if the overall limit, right, from the right and the left, is equal to the function level, right? Limit level is equal to function level. Bumping bellies equals, where they bump bellies is equal to the y value of the function. You have continuity. But of course you have to, that depends upon the fact that the function exists and the limit exists before you can really get to that, right? A function is considered continuous at its endpoint if the appropriate handed limit. So I showed you that example with the endpoint of x equals 0, right? I don't have to consider the overall limit, duh, because you're at an endpoint, so the overall limit is not appropriate. So you don't have to copy this down. I would, again, be suggesting that in your notes, you title your notes continuity and limits, and you write this down, and you maybe do an example, right? One of the examples that we had done on this screen, right? Or I'm going to do another one and remind you that only if you are asked to, right? Do you have to go all 3 steps? Yes, you do if you see the word prove, justify, explain, or show. You see those words, you need to go through and tell me you looked at the function value, you looked at the limit, you looked to see if those 2 values were equal, and you made a conclusion. Don't forget to make a conclusion. So if you think about a test writer, right, I can test a student on evaluating a left and right hand limit or evaluating an overall limit within this problem. If I ask a continuity problem, I'm also asking you if you can evaluate an overall limit, right, or an endpoint limit. So I can, right, I don't have to write a whole separate test question if I want to test to see if a kid can do that, as long as you write it out here. So please do show your work when you are asked. And how you are asked is, in this type of problem, prove, justify, explain, show. So you don't need to copy all of this, this down if you don't want to, because it's fairly self-explanatory, and no time on a test would we, lay it out exactly like this for you. But this is to just highlight the steps that you need to show. And again, also when you can skip steps, you don't always have to fill in every one of these values. For instance, look at x equals 3, right? At x equals 3, the function value is undefined. I don't have to do anything here. I don't need to consider this. I can just say no. Right? Again, the endpoints are kind of silly. If you see a closed circle on an endpoint, well, then you're continuous, right? The function value is -1. The limit from the Left is all I have to consider, is also -1. Those two values are equal, therefore I'm continuous at an endpoint, right? Endpoints are kind of silly questions. I guess I should say yes there. Yes, they are equal. So yes, I am continuous. Now look at 0. I can see that it's not continuous. I have a jump, right? I have a jump discontinuity here. So how do I prove it? X equals 0 exists and is -1. The limit does not exist. I do not have bumping bellies as I approach 0 from the right and the left. My range walkers do not bump bellies. Therefore, I don't have to consider this question because I stopped at D and E here. No, right? X equals 3, I stopped when the function was not defined. Look at number 2, I have a point discontinuity. I can tell that it's not continuous there. How do I prove it? The function level is at a height of 2. I do have a limit. I have bumping bellies there, but at a level of 2. Are those two values equal? 2 does not equal 0. Therefore, no. Okay, pretty simple, pretty simple. So some things that you don't have to worry, you might have to write out all 3 of those steps, but you don't really have to do any thinking, and you don't need a graph if you've got polynomials, because you know polynomials are continuous everywhere, right? I heart polynomials. I heart absolute value. I heart exponential functions. I heart most I heart sine and cosine. And I know where the only issue I have with tangent, cosecant, secant, and cotangent are at the places where they are undefined, and I know where those are. Everywhere else, I have continuity. I heart logs. Logs are continuous once their domain starts. Roots or power functions, right? Once their domain starts, if it's an even radical, or across their whole domain if it's an odd radical. And rational functions, I mostly love because I only have to, the only issue again is where, if I know where the denominator is equal to 0, I don't have to worry about really checking everything. I know it's continuous everywhere else, but at where the denominator is equal to 0. So take a look at this. Explain, right, why it's continuous on its domain. So on its domain, notice I don't ask you to prove a function is continuous on its domain. I only ask you to explain. So right now, if I ask you to explain at a point, that's different. But explaining on a domain, that's when you can kind of sort of think of that's the same as prove. But when I'm talking about an overall domain, right, overall domain, I'm looking at a function, right, that is not one of these, but it is a combo of these. Products, quotients, sums, difference, compositions, all of continuous functions are continuous, right? So as long as you've got continuous functions, you're okay, right? So, in any kind of combination of them. So look at what I have here. I have absolute value. Absolute value is continuous. Composed inside rational absolute value is a product, but it is a product of x, which is continuous, and sine x, which is continuous. Polynomial and sine. Then I have another polynomial, which is continuous. Although I have a rational function, so my only issue is where the denominator is equal to 0, but x squared plus 2 is a parabola that opens up and is above the y-axis, therefore never is equal to 0, and that's why this function is continuous on its domain. because all pieces of that function I don't recognize are continuous. The step function is not continuous on its domain because it is, right? Right, if you put numbers into here, jumps, right? It has a bunch of jumps. I didn't ask you to go through a formal, right, proof, right? So it is okay to just you recognize. This would never be a test question. This is just making, again, sure that you recognize the greatest integer function. Tangent x, why is tangent x not continuous for all reals? Notice this language because there are some that will argue that tangent is continuous over its domain. Yeah, go ahead and argue amongst yourselves. I could not care any less. Tangent is broken, and I know where it's broken. It's broken at all the pi over 2's, right? Tangent is sine x over cosine x, and cosine x is equal to 0 at your plus and minus pi over 2's, 1, 3, 1, 3. I'm not going to bother writing my pre-calc k and odd integer, blah, blah, blah. I just know. That's why. I'm explaining why. Again, these would never be test questions. This is just, again, trying to make sure that you can picture certain functions in your head. I don't expect you to picture that function in your head, but I expect you to know that since each piece is continuous, and that even though I have a fraction, the piece in the denominator will never equal 0, I don't have to worry about continuity at any value for f of x, that first f of x. All right, the intermediate value theorem is a theorem that doesn't involve any calculus, actually, but we're gonna use it for some of our reasoning down the road. And it really is a no-duh theorem. As long as you are continuous, and I don't have to be continuous everywhere, I just have to be continuous on some closed interval. If I am continuous between A and B, then I am guaranteed that the function takes on every range value between f of A and f of B. And you might say, well, duh. But notice that the function that I've drawn takes on some other values under f of A and above f of B. That's not guaranteed by the IVT. The intermediate value theorem guarantees, doesn't mean it's the only thing possible, but guarantees that at least one time every function value between f of A and f of B will be used at least once, right? It may be used values might be used more than once, and there might be, as this graph shows, values below f of A and above f of B that are used, but the IVT guarantees all of these red values are achieved at least once. So how will AP test me on this? Because they will never ask you for the formal intermediate value theorem. But they might give you, as part A of a problem or even a multiple choice, they'll say, given this discrete table of values, how do you know the function must have a 0 between -2 and 1? And the trap is for you to say, oh, look, the range values are negative, and then the range values become positive. Therefore, you must have hit a 0 in between here. But that's false. You do not have enough information to conclude, because these could just be points. The function might be points, or the function might jump like a step function. If f of x is continuous, if you get this information, then yes, you know you hit 0. If they tell you f of x is continuous and you see some negative range values and some positive range values, as long as you have continuity, you are able to conclude that you have hit 0 at least once. And when they ask you to justify, you are allowed to just say by the IVT. But you have to have been told or know that you are continuous first. You can't conclude if someone just gives you a discrete table of values. All right, continuous extensions. So this is where we were talking about the removable discontinuity. If you have a removable discontinuity, I can fix it, and I'm going to teach you how to fix it, and it feels like cheating. Fix it. Here's the vocabulary that you need. Extended function with a different name. And it is continuous over the removable discontinuity. So step 1, where is the removable discontinuity? And this is where prerequisite knowledge comes in. You have to be able to quickly take that function, factor it, and see where does it have a hole. Now I've given you the graph. You can see that there is a hole at x equals 2. You're not going to get this though. So you need to take the function x squared plus 6 plus x minus 6 and factor it. Factor the difference of two perfect squares in the denominator and realize that you can simplify the given expression because you have matching factors. And when you have matching factors, then you have a hole. There used to be a vertical asymptote at 2, but it got shrunk to an itty bitty hole. The infinite discontinuity at -2 could not go away. There's nothing to be done about that. I can't fix it, but I can fix the hole. So firstly, I found the hole. That was step 1, was at x equals 2, because that's the factor that canceled out. 2, find the height of the hole. The y value of the hole using the simplified function. So take your simplified function and plug 2 in. You can't plug 2 into the original function, but I can into the simplified function. 2 plus 3 over the x value of the hole, 2 plus 2, and I get 5 over 4. That's the y value of the hole. Now write your extension. And here's your template. Your extension function is not f of x, but it is f of x extended, right? Kind of think hair extensions, right? Extended. So you're going to write the original function here, original f of x. I want my new function to behave exactly like my original function, except at the hole. Don't equal the hole. X does not equal 2. So I know X cannot equal negative 2 as well, right? That's my vertical asymptote. I can't fix it. This is me going to fix the hole. At the Y value of the hole, plot the point 5 force, and now I have fixed the removable discontinuity. I removed the removable discontinuity with my extension function, right? And again, it seems a little bit like cheating, but I didn't name it f of x. I'm telling you it's not exactly f of x, but it behaves exactly like f of x, except not equal to the whole. It still has a vertical asymptote. Can't fix that. So again, your extension template looks like this. Extension template. You call it something different than the original. Extend. The first line is the original function, comma, x does not equal the x value of the whole. And then when x does equal the x value of the whole, over here you put the y value of the whole. And we'll practice this in our live session, okay? So don't worry, you shouldn't have too much problem with continuity. The IVT, the intermediate value theorem, is a little weird the way AP might ask you about it, so we'll practice that, and we'll practice continuous extensions in our live session. All right, see you then. Take care.